Reading week 9. This week's main physics idea was the topic of magnetic forces and flux. We looked at how a magnetic force on a single moving charge can be calculated using the equation F(b) on Q equal to Q, which is the charge, times velocity, cross product with the B field, which is magnetic field. And the direction can be determined using the right-hand rule, or the direction of the cross product of velocity and B field is going to tell us the direction of the magnetic field. And when there is a uniform circular motion of the charge, we know that the perpendicular portion of the dp over dt is the only thing that's changing, and that is equal to mv squared over r. And using this definition, we can rearrange the equation to calculate the radius of the circular motion, which is equal to be r equals to mv over magnitude of charge times the magnetic field. Then we also looked at the magnetic force on short current carrying wire, and this is using the same equation as we looked at for the single moving charge, but instead we are multiplying with the number of charges that we are applying the single moving charge equation to, and this leads to delta magnetic force equal to I current times the cross product of delta L and magnetic field. Then to understand flux, we use the flow analogy to look at the flow rate in a volume specified by height v times delta t, and area is delta a, and we make this to be equal to velocity times dot product with the normal unit vector times delta a. To calculate electric flux, we know it's the integral of electric field dot product with normal unit vector times dA. And similarly for magnetic flux, we just substitute the electric field with magnetic field to get the magnetic flux. I already knew how to do the right-hand rule, and this was handy to understand the direction of the magnetic force on moving charges, but I did not know anything related to magnetic force or electric flux and magnetic flux, and so this was very new to me. Something interesting that I learned is the calculation of non-uniform flux and how it is in the same format for electric and magnetic flux, and so we just substitute E field to B field or B field to E field to calculate whichever one we need. And the integral of flux was really similar to other equations that we used before. For example, we know that we can calculate a magnetic field or electric field on a point charge using integral of infinitely small amounts of single charges and adding them up to find it for a loop or disk or anything else. How this week's topic relates to my major is that magnetic circuit is made up of one or more closed loop paths containing a magnetic flux, as you can see on the right. And as we learned, magnetic flux is generated by permanent magnets or electromagnets and confined to the path. So it's interesting to see how magnetic flux relates to creating magnetic circuits. A confusing topic was the difference between electric flux and magnetic flux. And so flux is actually the presence of force field in a specified physical medium, or the flow of energy through a surface, and the number of lines in a plane that contains or intersects electric charge poles or magnetic poles are flux. And for electric flux, we know the total number of electric field lines that pass through a surface is equal to the flux, and it is a scalar quantity. And for magnetic flux, the magnetic lines of force passing normally through a surface is what matters, and the rate of change of magnetic flux is actually equal to the induced voltage around the surface.